Welcome, I'm Alexander Gerst, an astronaut of the European Space Agency. I'm talking to you from the International Space Station. My journey here aboard a Soyuz spacecraft from liftoff in Kazakhstan to the time we docked just took over about 5 hours. The video you're about to see contains some unique footage taken inside the capsule while it is in orbit and explains how the Soyuz safely reaches orbit and docks to the space station. Many other astronauts have taken the same journey, and some of them will also share their experience with you in this video. Have fun watching it.
Nine minutes ago, a Soyuz spacecraft blasted into orbit from Baikonur in Kazakhstan. It is now speeding around the Earth 30 times faster than a jumbo jet. It has a single purpose: to catch up with, rendezvous and dock with the International Space Station, located somewhere 400 kilometers above the ground. The astronauts just went through the last phase of the launch sequence, the separation of the Soyuz spacecraft from the rocket.
The finishing of the engine, or the shutdown on the engine, is pretty strong.
And immediately afterwards, of course, you float. It's really a very nice feeling that you know, yes, we are in space, we had a successful launch, now we are on the way to the space station. You can look outside the window, you see this magnificent Earth for the first time from above. It's really a great feeling.
And then just the absolute beauty of the sun coming up really quickly, illuminating, bursting into flame.
Now in their first orbits around Earth, at an insertion altitude of about 220 kilometers, the three astronauts in the Soyuz certainly have a wonderful view. But there is work to be done, as they are still hundreds of kilometers away from the ISS, their final destination. The International Space Station began life in 1998 and has been orbiting Earth about once every 90 minutes ever since. The orbital plane of the ISS is fairly constant, while the Earth is always rotating. Projecting the orbit of the ISS onto a 2D map, we see a series of intersecting curves. The mission control centers in Moscow and Houston constantly monitor the position of the ISS and can predict its expected location in the orbit for any given time in the future. This is important for determining when the Soyuz spacecraft launches. While it is technically possible to launch the Soyuz rocket at any time, it's most efficient to do so shortly after the ISS orbit passes over the Baikonur Cosmodrome in Kazakhstan. This shortens the amount of time to rendezvous and dock with the station from about 2 days to only 6 hours. This short rendezvous trajectory has been implemented since 2013. However, if the Soyuz rocket misses the necessary launch window or any of the upcoming engine burns do not occur as planned, the spacecraft has enough extra fuel to revert to a 2-day-long rendezvous. This happened in March of 2014 because of an attitude control problem, and thus the rendezvous was replanned to the formerly used long trajectory.
You take into consideration that there are some risks, some are worse than others, including the possibility of transitioning from a very short docking to a long docking, which was the standard until a year ago. We know the possibility, it's something that we are trained for. We know that the spacecraft has everything that we need for those 2 days, and we know how to react.
Rendezvous is defined as the sequence of maneuvers governing the approach of two space vehicles to one another. In most cases, one of them is the chaser, performing the maneuvers, in this case the Soyuz, while the second is a passive target vehicle, in this case the International Space Station. Ideally, both vehicles meet up safely at an exact pre-selected point in space and time. But how does the Soyuz achieve this? Well, the Soyuz has to climb from its initial insertion altitude up to the same altitude of the station, and then join and stay on this orbit. It sounds like a simple enough task, but it cannot be done in one single maneuver, starting from the insertion altitude. Calculations for the final docking are based on a precise initial Soyuz altitude, and unfortunately, the exact insertion orbit altitude is not known in advance because of some unpredictability in the rocket launch. Therefore, two maneuvers are used, with an intermediate phasing orbit in between. The phasing orbit is the basis for the final docking calculations. It is reached using the first maneuver, called a Hohmann transfer, named after a German scientist from the beginning of the 20th century. During the Hohmann transfer, the Soyuz has to use its engines twice. The first time is to leave its current insertion orbit shortly after launch and transfer up to the phasing orbit. The second time is to get the vehicle traveling at the right speed to stay on that orbit. The phasing orbit is lower than the ISS orbit by about 100 kilometers, and it serves a very specific purpose. It decreases the phasing angle, or the angle between the two spacecraft in their respective orbits. Here we see the Soyuz orbiting in the phasing orbit, depicted in yellow, while the ISS is orbiting in a higher orbit, depicted in green. The third, red orbit, is the insertion orbit the Soyuz has already left. Because the Soyuz is on a lower orbit, it will travel faster than the station. Therefore, the Soyuz uses this phasing orbit to catch up with the ISS. Depending on whether the long or short rendezvous approach is being used, the Soyuz will remain in this phasing orbit for close to 2 days or just a few hours, however long it takes to reach the desired phasing angle. Meanwhile, the crew haven't just been enjoying the views and weightlessness. They've been busy with leak checks and making sure systems are performing nominally. Then, they issue the command for docking probe extension in advanced preparation for the final docking sequence. As soon as the pressure integrity of the vehicle is confirmed, the Mission Control Center gives the go-ahead for the crew to loosen their seatbelts, open their helmets, and take off their gloves. Once they reach the phasing orbit, the crew finally have some well-deserved downtime, especially those completing the 2-day-long rendezvous trajectory.
There are what we call 5 DEF orbits. It's 5 orbits in which the crew cannot have contact with the ground because the orbit of the space of the Soyuz is not passing over Russia, and you only have contact with the ground when you're passing over Russia with the Soyuz. So you're completely on yourself. And so it's actually a nice time for the crew because you cannot be disturbed, nobody can give you tasks, you can do whatever you want.
Luckily for the astronauts, the Soyuz is designed so that they are not confined to their seats for the entire trip. Though small, the spacecraft allows the astronauts to move freely between the accessible modules. The Soyuz has 3 compartments: the orbital module, the descent module, and the instrument compartment. Each compartment has a different architecture and a specific purpose. The orbital module, or living compartment, is equipped with sleeping bags, food, and a toilet.
So here we are in the Soyuz. This is what we call the BEO, the living compartment, Bitovoy Otsek in Russian. It also has a little bathroom. It's not as good as the other bathrooms, so we try not to use it too much. It has drinking water in it if we need something to drink. And then, of course, it's filled up with a lot of cargo for us.
The instrument compartment, not accessible to the astronauts, houses the oxygen and propellant tanks, thrusters, the onboard computer, and a number of sensors. From the descent module, the 3 crew members monitor all information about the spacecraft and the ISS from ground data, the onboard computers, and an optical display of the view from a periscope mounted on the outside. For the second orbital transfer and the final rendezvous maneuvers, the astronauts return to their seats in this module. The second orbital transfer brings the Soyuz from the phasing orbit up to the ISS orbit. It's called a bi-elliptic transfer and requires 3 engine burns instead of the Hohmann's 2. From the phasing orbit, the first two burns bring the Soyuz up to the ISS orbit. The third burn gets the vehicle traveling at the correct speed to stay in the ISS orbit. The burns of the bi-elliptic transfer are calculated based on the precise altitude of the phasing orbit, and consequently, if the phasing orbit is too high or too low, the Soyuz will not meet up with the ISS as expected. The reason for using a bi-elliptic transfer here instead of the Homans is that the Soyuz will not only reach the correct altitude in the close vicinity of the ISS, but also with exactly the desired speed. Despite these precise maneuvers, what if the thrusters fail to slow down the Soyuz and the vehicle travels too fast as it approaches the ISS? This could end in disaster, with the Soyuz crashing into the station instead of docking. To prevent this from happening, the Soyuz performs an additional side burn. This changes its orbital plane slightly and makes a collision between the two vehicles impossible. Throughout the rendezvous process, the Soyuz onboard computer continually determines the position and velocity of the Soyuz itself and of the ISS. To do so, it uses measurements provided by the ground controllers and a radar system called the KERS. In this way, all of the burns during the rendezvous are calculated and automated by the onboard computer.
So Soyuz navigates in space and looks for the station with a special radar system, which is called KURS. This gets turned on at 400 kilometers from the station. It looks, and usually it sees the station and locks into the station at around more or less 180 kilometers. At that distance, we really don't see the station. It's probably, even if you could see, it's probably similar to any of the stars that are up there in space. But you see on the screen the lock, the software indication that the radar locked into the station.
The third and final burn of the pre-mentioned bi-elliptic transfer is very important because it sets the vehicle up for its near-ISS rendezvous procedures that will lead to docking.
When you do a normal burn in the space station, well, the vehicle rotates to the correct attitude at 2 degrees per second, and then it takes about 8 minutes to start the burn. When you're close to the space station and you have to brake, of course this would not work. So then the vehicle all of a sudden starts rotating quite fast, 3.5 degrees per second, and only just after that, 50 seconds after that, you already have the burn. And once the burn is completed, immediately the vehicle starts rotating again to the normal orientation. And the crew has to monitor this quite intensely. And these are really high peaks of workload to see that everything is okay, the rotation is going okay, you know that you have the burn values were okay, you rotate back, and then you see back the space station in your main display.
We could see it first a dot, a little bit brighter than the other star in the sky, and then little by little we started to see like a little spider first with all the solar arrays and everything, and then it was apparent that there's a huge outpost was right there in front of us.
During this stage, the crew commander, sitting in the middle, gives vital information and instructions to his crewmates. Their workload has increased. Many parameters need to be checked and systems activated. Days before launch, a team of flight dynamics experts at the mission control centers in Moscow and Houston determine the ideal position and orientation of the ISS, based on a careful analysis of the constraints that could affect these final stages of the rendezvous timeline. First, there must be adequate lighting conditions at the time of docking so that the Soyuz crew can see the ISS without being blinded or blocked by the sun.
It depends if the station is illuminated, is in the sun, then you can see it even if you are relatively far away. But if the station is not in the sun, then you cannot see it even if you are close.
Additionally, major temperature fluctuations of ISS elements, such as the solar arrays, must be avoided to prevent structural deformation. Finally, there must be clear communication pathways between the ground, Soyuz, and ISS. The rendezvous is a fully automated process performed by the onboard computer. However, the commander still takes the hand controller just in case there is a need to perform a contingency manual docking.
If you don't see the space station or something happens at that moment, then you might have to take manual control. And so you have to remember very well, where is the space station now? What are the actions that I'm going to take? And this is really the intense moments that happen.
Manual docking requires two hand controllers to pilot the vehicle, a left one that controls translation and a right one that controls rotation. The crew are thoroughly trained in these manual docking procedures, even training until the very last days before launch in Baikonur. Besides contingency docking, the crew might also utilize their manual control training during redocking maneuvers. The ISS is constantly visited by manned Soyuz vehicles and other unmanned supply ships. Sometimes it's necessary to undock an attached Soyuz and redock it to another port on the ISS to make room for one of these new ships. Luca Parmitano did this as part of Expedition 37.
My crew was one of the few crews able to perform a manual docking, and it went very smoothly. We were excited because it's something that we trained on for a long time, and we were able to do it.
Apart from this case, a routine docking sequence is fully automated, and the crew's main task is to monitor the systems to ensure nominal procedures. At this stage during routine docking, the vehicle's relative speed continues to decrease, as does the distance between the two.
400 meters from the space station, a new phase enters. This is the phase what we call fly around.
During this phase, the vehicle is actually not pointing at the desired docking port, but at either one of the station's Kurs antennas. It's only when the vehicle reaches its 150-meter station keeping mode that the orientation changes to point at the selected docking port instead. The Soyuz then performs a second fly-around to line up with the docking port, while keeping a distance of 150 meters. Once aligned with the docking port, the crew issues the command for the last stage, the final approach. The Soyuz computer display uses data from Kurs to provide the astronauts with pertinent information about the rendezvous and docking maneuvers. Among other readouts, the distance from the ISS is displayed, here showing 5 meters, as is the relative velocity during the approach, currently 10 centimeters per second. This and other information is overlaid on the video feed, used to track alignment of the target.
5 meters, 0, 1, 2. Target in the center, crosshairs aligned.
By for contact and capture of the International Space Station.
Contact occurs as soon as the probe touches the entrance cone of the docking hatch. Then, the thrusters give the Soyuz an extra push, and the docking mechanism ensures capture.
Of accelerations or rotations, standing by for contact. Contact. Mechanical capture.
And contact and capture confirmed.
I think this is where the impact was. So I'd say about 4 to 5 inches off center. It's pretty good after traveling for a couple million miles.
The probe retracts and you get the two vehicles closer to each other, and then when they are very close to each other, less than 2 to 3 millimeters, the hooks start closing. And it's when these hooks are fully closed that can take an enormous pressure, because they can withstand 16 tons of force, each of the hooks, and you have 8 hooks on the Soyuz vehicle.
This is still not enough, because there might be something inside your ring, some dirt, some debris that is not allowing for a good seal. So there is a series of vacuum and depressurizations done in a very astute manner that verifies that each one of these compartments is actually sealed tight. Only at that point, and by the way, all of this takes, I would say, an hour, 1 to 2 hours. Only then, when everything is proved to be fully sealed, only then you can open the hatch of the station, the hatch of the Soyuz, and the crew can actually go into the station.
And what we usually do is we knock on the hatch that goes on the side of the space station. They knock back we know that there's somebody else on the other side.
And the hatches between the Soyuz spacecraft and the International Space Station opening at 11:14 p.m. Central Time.
Then it's hugs and smiles for everybody.
The astronauts are now safely on board the International Space Station, their home for the next 6 months.